Student, let next start with the next lecture, that is thermodynamics heat engine. Students, heat engine is a device, right, which converts heat energy into mechanical energy in a cyclic process. Let's take a layout diagram to understand that, right? Students, source means it's a heat reservoir, we say. That means it is having some temperature T1. It is supposed to have definite thermal capacity. Yes, sir. No? From where we can take the heat and we can utilize that heat. Some work will be done. Then after that, some heat will be also rejected. Correct. So that means this is source and this is sink. Source means it's a heat reservoir, right? Sink means it's a heat reservoir at a lower temperature. This temperature is T1, this temperature is T2, T2 is lower, right? And here heat engine or working substance. What is that? So it's working substance is any solid, liquid, or gas which performs mechanical work when heat is supplied to it, right? For example, a mixture of a fuel vapor and air is used in a gasoline or a diesel engine. You know, in diesel engine we mix fuel and air, right? Or steam in steam engine also. So that is the heat engine. It is taking some heat, combining, doing the work, then also leaving some heat, right? And student here, simply there is a it is having a working principle. But I'm coming to directly the work done, right? Let the net work done by the heat engine in carrying the working substance through a cyclic process will be how much, students? That work done is equal to how much? Change in heat energy, that is Q1 minus Q2, correct? Q1 was given, some work is done, then Q2. Q1 is heat supplied by the hot reservoir and Q2 is the heat rejected to the cold reservoir, right? Q1 क्या है? Q1 is heat supplied by hot reservoir VOIR, and Q2 is, students, heat rejected to cold reservoir. Right, that is sink. And student, if you are interested to find the thermal efficiency of the heat engine, that we want to find what is the thermal efficiency of this engine. Thermal efficiency, that means output by input. Thermal efficiency of heat engine, that is eta is equal to total work done divided by how much heat is supplied. We'll do examples on that to understand, right? That is total work done by Q supplied. And you know, student, work done, total work done is equal to how much? Q1 minus Q2. That is equal to Q1 minus Q2 divided by Q supplied means Q1 into 100, right? And making little modification, we can make 1 minus Q2 by Q1 whole into 100, correct? Yes or no, students?
Yes, sir.
In this way, we can find the efficiency of the heat engine, right? We'll see this application in refrigerator and heat pumps also. We can find this application in refrigerator and in heat pumps also, correct? Yes or no? And with this limitations of the first law of thermodynamics as there also. Because in first law, student, it does not indicate the direction of the transfer of heat. In first law, whatever the questions we have done, we don't know in which direction the heat is getting transferred, right? And it does not tell anything about the conditions under which heat can be converted into mechanical energy. That is also not given in first law. And first law also does not indicate the extent to which heat energy can be converted into mechanical energy. Just we are calculating what is dq, du, and dw, right? But those things were covered in second law of thermodynamics, right? So what is there in second law of thermodynamics? Next, let's see. Next, give heading. Second law of thermodynamics. Second law of thermodynamics, right? Yes or no? Students, here there are many laws. Let one by one I'm saying in brief the laws. Kelvin Planck statement. What was about that? Kelvin Planck statement, right? What was Kelvin Planck statement? Student, Kelvin Planck statement told that no process is possible whose sole result is the absorption heat from a reservoir and complete conversion of the heat into work. That means, students, see, there are many processes. There are many processes in which heat energy is conserved. Yes or no? But the principle which disallows such phenomena. Well, in first law of thermodynamics, as you discussed, let the first law of thermodynamics is called second law of thermodynamics. Why? Because it can be stated in the number of ways. Like what Kelvin and Planck statement told, it is impossible to construct an engine. We cannot construct an engine which will produce no effect other than extracting heat from a reservoir. That means it is taking some heat means some work will be definitely there will be some work done, right? So Kelvin Planck statement was like this: it is impossible, right? It is impossible to construct. It is impossible to construct an engine which will produce no effect other than extracting heat from a reservoir. Right? And performing an equivalent amount of heat. And performing an equivalent amount of work. Right? This is Kelvin Planck statement. What was that actually? Students, this is applicable to heat engine, right? What it indicates? It indicates that working substance. That means in a operating cycle, we cannot convert all the heat extracted from source into mechanical work. There will be some heat, there will be lost. Yes or no? That means we are giving some fuel. You are doing some, let the wheel is moving in the bikes. Some heat is also getting transferred, students. Some smoke is getting ejected. Yes or no? That was the Kelvin Planck statement, correct? And there is another statement, student, by Celsius on second law of thermodynamics. He gave a statement, right? That is Celsius statement, right? Class CLAU, Classius, SIUS. What statement he gave? Students, it is impossible for a self-acting machine honored by an external agency to transfer heat from a body to another higher temperature. Means without the body, without taking the help of a body, we cannot increase the temperature from one to other, right? So right here, it is impossible for a self-acting, machine, correct, unaided, unaided by any external agency to transfer heat from a body to another higher temperature. From a body to another higher temperature. Right? This is the two laws, right? And what is the significance of second law? Simply I am saying the second law of thermodynamics puts a fundamental limit to the efficiency of heat engine, right? There is coefficient of performance of a refrigerator, right? And the efficiency of a heat engine can never be unit. That means whatever the energy we are giving, all the energy cannot be converted into output, right? This term implies that the released to a cold reservoir can never be made zero. Some heat will be lost. And the coefficient of performance of refrigerator can never be infinity also. That means that the external work can never be zero. That means, students, in refrigerator, heat supplied by total work done. So there is that we're taking the efficiency. That efficiency is known as coefficient of performance. This eta is known as coefficient of performance, right? This is about second law of thermodynamics and Kelvin's Planck's statement and class-year statement, right? Next, let's see, student, Carnot engine, right? So let's see the another application, Carnot engine, right? It's an ideal reversible heat engine that operates between two temperatures, T1 source and T2 sink, right? Source, and we'll see what are the different cycles in this. There are four steps. That is for an isothermal expansion, for an adiabatic expansion, when isothermal compression, right? This is what seeing in the graph, pressure and volume graph. This is pressure and this is volume, right? This line is temperature T1, this line is temperature T2, right? Different points have taken 1, 2, 3, 4, right? So student, you see here 1 to 2, 1 to 2 is isothermal expansion, right? That is isothermal expansion. That means students, Q1 heat is absorbed from source and W1 work is done in the gas by in isothermal expansion, which takes the states from P1 V1 T1 to P2 V2 T1. Isothermal temperature remains same, student. That's why isothermal, right? And here in this isothermal expansion, you can calculate the work done, students. W1 is equal to, you can write that is Q1, that is equal to nRT ln V2 by V1, and that is positive, correct? Delta U is equal to 0. This is step 1, correct, students? And step 2 is from 2 to 3, point 2 to point 3. See here, step 2 is point 2 to 3. 2 to 3, what happens, students? See, this is adiabatic expansion, heat remains same, temperature changing but heat remains same. This is known as adiabatic expansion. Today morning only, that's why we did one numerical, right? Adiabatic expansion, student, that means no change in heat, Q is equal to 0. So directly work done is equal to, students, minus change in internal energy, that is nr delta T divided by gamma minus 1, right? Yes or no? That means here P2 V2 T1 to P3 V3 T2, it is changing, right? We can calculate, and this is the area under B, this area. We can find this area. Okay, this area is going to be, we can find, we'll do the numericals on that, right? Then student, from 3 to 3, this is 0.3, this is 0.4, 3 to 4, right? 3 to 4 is step 3. 3 to 4, student, that is isothermal compression, right? Heat is constant but compression here, isothermal compression. So the same way as step 1, this is isothermal expansion, but here compression. Only work done will be negative, but same, rest is same. That is delta U is equal to 0 and W2 is equal to Q2. That is nRT ln V4 by V3. That is negative work done, right? Yes or no? Then at last, students, see 4 to 5. This is also, this was adiabatic expansion, but this 4 to 1 will be adiabatic compression, right? So write step 4, that is 4 to 5 process, right? That is adiabatic, right? That is adiabatic compression. So adiabatic compression, adiabatic means no change in heat, 0. So W4 is equal to minus delta U, that is equal to nR delta T divided by 1 minus gamma, right? Yes or no, students? So student, in Carnot cycle, I'm seeing you the final thing. In Carnot cycle, right? In Carnot cycle, see Qt, you see here. Q1 by T1 is equal to Q2 by T2. Q1 by T1 is equal to Q2 by T2. That is equal to W divided by T1 minus T2. So if you're finding the efficiency, then it will be how much? What is the total work done by what is Q supplied into 100? And that is nothing, only Q1 minus Q2 divided by Q1 into 100, right? So that is equal to 1 minus Q2 by Q1 into 100, correct? That is equal to 1 minus T2 by T1 into 100. because Q2 by Q1 is equal to T2 by T1. In this way also you can find the efficiency of the Carnot cycle, correct? Are you getting? Just I'm saying in this thing, all those things, because we will do numericals on that basis. You will get the questions directly on this basis. This chapter is not difficult. Yes or no? So you can apply this in Carnot theorem also, right? What is Carnot theorem? What is refrigerator or heat pump, correct? And at last you can also find what is entropy, right? There is a term entropy in a very small process, right? In a very small process, an infinite small process, students, system changes from one equilibrium state to other equilibrium state, correct? If delta Q is the amount of heat transferred, yes or no, then entropy is equal to the amount of energy for the reversible process, correct? So all this Carnot theorem, refrigerator or heat pump, right? Coefficient of performance, all are there. Yes, so we can understand now. So tomorrow we'll do examples on this tomorrow morning on this, yes or no? How to find everything on this web. We'll do another examples tomorrow. Then we'll go for the next chapter, kinetic theory of gases, correct?